For our project, we aim to create a sterilizer for low to middle income countries for instruments used during childbirth. My name's Juliana, and I'm joined by my group members, Brian and Alba. Sub-Saharan Africa has the highest neonatal mortality rate in the world, with 27 deaths per 1,000 live births. This is 43% of global newborn deaths. When non-surgical instruments are used to cut the umbilical cord of a newborn baby, tetanus can occur, which can have many lifelong effects. Low to middle income regions such as sub-Saharan Africa need a low cost and reliable way to sterilize instruments used in childbirth because contaminated instruments can cause diseases such as tetanus or even death for mothers and neonates. With our design, we strive to create an autoclave that is low cost, easy to use, doesn't require electricity, and can be portable so those all across the sub-Saharan region can have access to a safe and healthy birthing process.
For our autoclave, we have decided to use a gravity steam sterilization. Gravity autoclaves are the most common kind of autoclaves for hospitals because of their simplicity and dependability compared to other autoclaves. In a gravity steam sterilizer, steam is produced and passed into an autoclave chamber. Since air is heavier than steam, the air then exits the autoclave through a drain port, or in our case, a steam valve. So there is only steam left in the autoclave. For our powering system, we have decided to use a solar parabolic dish. The solar parabolic dish consists of the receiver, the solar reflector dish, and the supporting structure. The advantages of the solar parabolic dish are the high concentration of sunlight, the high energy efficiency, and its compact design. For our steam sterilizers, the design consists of the parabolic dish, which is supported by a cart with wheel system, which can be easily transported, but also directed into the sun's direction. It consists of the steam sterilizers, which is a 7-liter pressure cooker that can accommodate up to 13 small surgical kits per load. The parabolic dish has an area of 2 meters squares and a diameter of 1.6 meter and a focal distance of 0.4 meters. It can supply energy sufficient for 30-minute cycle, achieving a minimum temperature of 132 degrees Celsius, which meets the standard requirements.
For our autoclave material, we decided to use aluminum. Typically, stainless steel is used because of its high melting point and structural stability, but because our autoclave only reaches 103 degrees Celsius, and aluminum's melting point is 660 degrees Celsius, aluminum is a good fit for our autoclave. It also is lighter than stainless steel and has a higher heat conductivity. For our supporting structures, we chose to use steel because of its strength and resistance to wind, and we decided to coat our absorber surface in black paint because of its high absorptivity. Here we can see a SolidWorks model of our pressure cooker sterilizer design with a safety valve, steam release valve, and pressure gauge. Here we have a 360 view of our parabolic dish along with our steel supporting beams and our aluminum autoclave. For our total cost, considering the water needed for one cycle, the steel support bars, the aluminum for the autoclave, the black paint, and the parabolic dish, our total comes to around 253 pounds.